Imagine a universe of computation so vast it could solve problems our best computers would take eons to crack. This is the promise of quantum computing, a revolution that rewrites how we process information. By harnessing the strange laws of quantum mechanics, we're not just building faster machines, we're unlocking new ways to understand reality. The quest to build a quantum computer is one of the grandest scientific adventures of our time. Quantum computers could help us design new medicines, discover novel materials, and untangle the complexities of our world. To answer these challenges, we need a tool that speaks the language of quantum physics. The rules at the quantum level are bizarre. Particles can be in multiple places at once and be mysteriously linked across distances. Now we're learning to control this weirdness, turning paradox into processing power. Let's embark on this journey, from the familiar world of classical computers into the mind-bending quantum realm. Before we dive into quantum, let's ground ourselves in the world of classical computing. Every device you use, phone, laptop, tablet, operates on bits, ones and zeros. A bit is like a light switch, either on or off, forming the bedrock of all classical computing. Billions of microscopic switches called transistors represent these bits, flipping at incredible speeds. Classical computers solve problems by checking each possibility one by one, like searching for a grain of sand on a vast beach. This step-by-step process powers the digital age, but some problems are just too big. For certain challenges, like simulating complex molecules or breaking encryption, the number of possibilities grows exponentially. Even the fastest supercomputer would take billions of years to solve them. The universe of bits and bytes, as powerful as it is, has a boundary. To go beyond, we need to enter a realm of richer possibilities. Now we enter the quantum sea, where the fundamental unit is the qubit. Unlike a bit, a qubit can be 0, 1 or both at once, thanks to superposition. Imagine a spinning coin. While in the air it's both heads and tails. Only when it lands do we see a definite state. This allows quantum computers to explore many possibilities simultaneously, creating immense parallelism. With just a few hundred qubits, a quantum computer could represent more states than atoms in the universe. Then there's entanglement. When two qubits are linked, their states are connected no matter the distance. Measure one, and you instantly know the state of the other, even across galaxies. Entanglement weaves qubits into a powerful computational fabric, enabling quantum algorithms to perform feats impossible for classical machines. By manipulating these entangled superpositions, quantum computers can zero in on the right answer. It's computation that leverages the very structure of reality. What truly separates quantum from classical computers is how they process information. A classical computer is like a scholar reading one book at a time in a vast library. A quantum computer is like reading every book at once, thanks to superposition. It's not just faster, it's a different paradigm, navigating a universe of possibilities. Quantum computers are specialized tools for problems classical machines can't touch. Think of it like the difference between a car and a rocket. You need a rocket for the moon. For example, factoring large numbers, a task that underpins internet security, takes classical computers eons. A quantum computer using Shor's algorithm can solve it in a fraction of the time. Classical computers crunch data. Quantum computers reveal hidden patterns in the universe of possibilities. The promise of quantum computing is immense, but the journey is just beginning. Qubits are fragile. Tiny disturbances can destroy their quantum state, a challenge called decoherence. Most quantum processors must be kept colder than deep space to function. We're in the noisy, intermediate-scale quantum era machines with dozens or hundreds of qubits, not yet outperforming classical computers. But the potential is huge, simulating molecules for new drugs, optimizing financial markets, discovering new materials, and more. The future will likely see classical and quantum computers working together, each tackling what they do best. As we overcome these challenges, we'll unlock more of quantum's power, learning to speak the universe's native language. The next chapter of innovation is being written at the quantum level.